Hello, welcome. My name is Sav. I'm a VCE Physics Specialist at Complete VCE Education. Today we'll be going through the solutions to this Unit 3 AoS 33 mock SAC that we tutors created ourselves. Now, if you have not attempted the SAC yourself, then please feel free to go to the description and download the SAC for yourself and attempt it before returning back to this video. Now, as I understand it, your Unit 3 AoS 33 electromagnetism and electricity transmission SAC is coming up quite soon in the next couple of weeks. So hopefully this SAC serves as a great revision for you before your actual SAC. Now this paper has 15 multiple choice questions and 7 short answer questions with the total time being 100 minutes. So it's a fairly long SAC. Most SACs from schools are only 60 minutes long. But this means that there's ample opportunity for you to practice. Okay, so without any further waiting, let's get started with question number 1 in the multiple choice. So, question 1. Transformers are an essential tool in electricity transmission and manipulation. However, they cannot be used with DC electricity. Select the most correct explanation. Okay, so we know that transformers, they cannot be used for DC electricity because they rely on electromagnetic induction to function, right? So if there's no change in the current, then there won't be any change in the magnetic flux, and therefore you won't have any induced EMF. So in this case, let's see which option correctly describes this. So option D, transformers rely on a changing magnetic flux, typically provided by an alternating current. That would be correct. Question 2, a power company is determining the energy usage of a particular home. They find that it receives a peak voltage of 339 volts. What is the RMS voltage? Well, we have to use the RMS voltage formula, which is given in the formula sheet, and you should end up with roughly 240 volts for this, which as expected is less than the peak. So please note that the RMS value should always be less than your peak value, since RMS is a form of an average, and an average data value must always be less than the maximum. Okay, question number 3. A current conducting ring is placed in a magnetic field, as shown below. If the circumference of the ring is 30 centimeters and the magnetic field strength is equal to 1.5 Tesla, so that's B, here's the circumference. What is the magnitude of the magnetic flux that's passing through it? Answer this to the correct number of sig figs. Okay, so first of all, we need to give our answer to 2 significant figures because the lowest number of sig figs in the data values given are in 2 sig figs. Anyways, for this question, we have to first of all obtain the area using our circumference. So this is a bit of a geometry question. Hopefully you guys know that circumference is equal to 2 pi r. So we have to first of all figure out the radius. And so we'll say the circumference is 0.3 meters divided by 2 pi. And that should give us, if I do this real quickly, that should give us 0.048 meters. And from here we can figure out the area. So therefore the area is going to be pi r squared. So we can plug in the numbers and we can obtain the area. So quite a few calculations in this question. And we will get 0.0072. Now this is just the area, guys. We must now multiply this area by the magnetic field strength to obtain the magnetic flux. So 1.5 times 0.0072, and that will give us 0.011 Webers, which is option A in this case. Okay, next question. Moving on. Small toys such as RC cars are often powered by DC motors, such as the one pictured. Alright, so the single coil ABCD is a perfectly square in shape and has side length of 3.8 centimeters. The magnetic field is 21.5 Tesla. Okay, so if the current were to flow from A to D, in which direction would the coil spin? Interesting. Okay, so this is a DC motors question, guys. So this is coming from the previous AoS study. And in this case, we know that our current is going to flow from A to D. It's going to flow like this, in this clockwise manner as viewed from above. Now you can select any side. Let's select side AB and figure out the direction of the force on this side. Now to figure out the direction of the force, we have to use the right hand palm rule or the right hand slap rule, as some textbooks call it. In this rule, the fingers represent the magnetic field, thumb represents the current, and the palm represents the magnetic force. So here, if we do this real quickly, I can take out my right hand, you guys can follow along. The thumb should be pointing into the page since current is going from A to B. Fingers should be to the right, and palm we can see is facing downwards. And therefore AB is getting pushed down. The magnetic force acting on it is downwards. And you can repeat the exact same thing for CD as well. However, the magnetic force should be in the opposite direction. It should be upwards since the current is in the opposite direction. So hence we can see that our coil is going to rotate anti-clockwise. Question 5. The DC motor is being fed a 4.5 volts from a battery. What is the magnitude of the maximum magnetic flux experienced by the coil in rotation? Now this value, guys, over here is not really important, okay? It's actually just there to confuse you. The magnetic flux is the measurement of the amount of magnetic field passing through an area, and that's nothing to do with the voltage. So it's only related to the orientation of the coil. And the maximum flux will occur at the vertical orientation, when all of the magnetic field lines are able to penetrate through the area of the coil. So in this case, we can use the side length of 3.8 centimeters to figure out the area and then figure out the magnitude of the magnetic flux at this point. So magnetic flux is going to be B times A, and that's going to be equal to 21.5 times 0.038 squared. And we can do this with the calculator, and that should give us 0.031 Webers. Perfect. All right, so some questions can give you unrelated values, like the 4.5 volts, which is not needed in our calculations. Question 6. If the current were to flow from D to A, which direction will be the induced magnetic force on the side BC? So now the current is flowing from D to A. So let's remove this. And now we're saying the current is flowing in this manner. So guys, you can repeat the exact same procedure as before. You can figure out the magnetic force inside BC. Now, side BC here is parallel to our magnetic field lines. So there's one small difference between this question and the previous questions that we've done. You can't actually use the right-hand palm rule for this because the current is parallel to the field. Because of this, the magnetic force will not exist on that side. Question 7. The motor is consuming 5 watts of power. What is the magnitude of the force acting on side BC under normal operation? Okay, very interesting. So, from the power, guys, we can figure out the current. Okay, so we can calculate the current from this power that we're given. In this case, we have to use the 4.5 volts value and the 5 watts value. So we know the power, we know the voltage, and we're looking for the current, because we know the current is going to then give us the magnetic force. Okay, so power is equal to current times voltage. From here, we can say that current is equal to 5 over 4.5. And we can use these numbers to obtain the current 1.11 amps. Afterwards, we could then plug this formula, or plug this value, my bad, into the NILB formula for the magnetic force. Now, in here, the number of turns of wire, N, have not been given. In such a case, when N is not given, N is equal to 1 by default. So you will multiply 1 by 1.11, so on and so forth, by the length, which we know is 3.8 centimeters. Multiply this by 21.5, and that will give us the answer. All right, so we will get 9.91 newtons. Okay, perfect. Question number 8. Why do the calculations involving AC electricity typically utilize root mean square? Okay, so for this question, we have to think about what the RMS really represents. The RMS, guys, root mean square, is used in statistics, frankly high-level statistics, as a special type of average. I'm sure you guys have studied mean, median, mode, range in statistics. You guys have learned about those quantities. RMS is a more advanced statistical quantity that we use to take a type of average of our data. Now, let's have a look through these options. AC electricity is special and thus necessitates its own unique formulas. Well, we know that's just not true. It is special, but that doesn't mean that it necessarily needs its own formulas. It's not an accurate representation of what's happening. B, averaging out the peaks of AC does not work since the result will always be 0. Okay, this is a correct answer. We can't just take a regular average, okay? Because if you have a look at your EMF or voltage graph for your generators, it's like a sine graph. And the positive voltage values will cancel out with the negative voltage values if you try to take a direct average. Okay, so a direct average will always yield 0. And that's not a useful quantity for our analysis. Okay, we can't just say that the average is 0 and let's just use that in our calculations. That won't work. We have to therefore use a very special type of averaging procedure. Okay, moving on. Question 9 to 11. So, a complete VCE power generation has put plans into progress to construct the first electrical transmission system as depicted in the diagram above. So they choose to utilize a step up and a step down transformers of ratios 5 to 23 and 6,325 to 3 respectively. Very big ratios. Now the 6 megawatt generator behaves like a typical alternator. Okay, so alternator, we know this means it has slip rings. Okay, just as a side note, experiences a change in flux of 55 Webers per quarter rotation. Let's annotate that. Now, if a 20-turn coil is being fully spun with a frequency of 50 Hertz, what is the alternator's output voltage? Great. Okay, so first of all, we have the number of turns of wire, we have the frequency. Okay, we have the change in flux. We need to now figure out the time per quarter rotation using the frequency. So we know, guys, the time per quarter rotation is going to be equal to the period over 4. Now the period is going to be equal to 1 over frequency, which is, in this case, just 1 divided by 50, 0.02 seconds. Therefore, delta t is going to be this value divided by 4, which is 0.005 seconds. Now we can plug this into our EMF formula, and we should get the answer, which should be 220 kilovolts. Okay, that will be the answer for this particular question. All right, moving on. So let's have a look at question number 10. So in this question, we have to first of all figure out what is the voltage that our generator has outputted. So we know the voltage is 220 kilovolts, but let's convert this to our volts. So we have 220 times 10 to the power 3 volts. Now, we know the voltage, we know our power, we can then figure out our current. So power is 6 times 10 to the power 6. We can divide this by our voltage, and we should get, as our answer for the current, 27.27 ... amps. So this, guys, is going to be the current that is outputted by our alternator. However, this current is then going to flow through the primary coils of the transformer, and it is then going to transform into a new current. Okay, now we know that the ratio of the number of turns of wire is 5 to 23. So now let's use our ratios formula. So we know that I2 over I1 is equal to N1 over N2. Now, N1 over N2, that's 5 over 23. And we can now multiply this fraction by I1. So we will end up with 5.929 amps. Okay? And afterwards, we can then use our power loss formula. P loss is equal to I squared R. Keep in mind that the resistance is 10 here. And we'll get, as our answer, I squared times 10. So we'll end up with 351.5 watts, which will be 0.35 kilowatts. Okay, perfect. All right, so question 11. The devices in the city receiving this power require it to be DC rather than AC. So for this, the answer is A rectifier. Now this is actually beyond the VCAR course. So not something they need to really focus on, but that's the answer, option A. All right, question 12. How could the power loss be minimized in electricity transmission for the same amount of input power? Select the most correct answer. Okay, A, transmission lines could be made of longer wires. That will increase the resistance, right? Which will increase the power loss. So that wouldn't work. B, transmission current through the cable could be increased. Not quite, because we know that our power loss is actually given by I squared R. So the greater the current, the greater the power loss across the lines. C, the transmission voltage of the cables could be decreased. Not quite, because, well, if voltage goes down, guys, then your current has to go up, and therefore the power loss has to go up. Okay, voltage and current are inversely proportional to each other. The transmission lines could be made of thicker wire. Yes. So if the transmission lines are made of thicker wire, then this will reduce our power loss, since this will reduce our heat loss or heat dissipation through the transmission lines. Okay, question 13. What is the name of the rotating device depicted above? Interesting. So in here, we know that we have a split ring commutator. And the split ring commutator is connected to a coil. The split ring commutator, guys, is going to be allowing for a DC output. So this must be a DC generator. Now it cannot be a motor, guys. The reason it's not a motor is because a motor requires input electricity. You must be giving electricity to a motor for it to work. You can't be getting electricity out of it. Can you guys notice how we have a load, we have a light globe that's going to be consuming electricity in the circuit? We don't have a battery. If the light globe was replaced by a battery, then this would be a DC motor setup. Question 14. What direction will the induced current be? Okay, so for this particular question, we need to have a look at our Lenz's law. And when we use Lenz's law, we have to think about first of all, the initial change in flux. Second of all, the direction of the induced magnetic field. Third, the direction of the induced current. And please follow the checklist step by step whenever you are using Lenz's law in your questions. So here, for the first step 1, okay, after giving the definition of Lenz's law, we can say that the initial change in magnetic flux as our coil rotates clockwise would be increasing to the right. Increasing to the right. All right, guys. So our coil is going to go from horizontal to vertical. And so when our coil goes from horizontal to vertical, the magnetic flux will be increasing to the right. That's step 1. Step 2, the induced magnetic field. The induced magnetic field should be to the left, okay, in order to oppose that increase. Now, the induced magnetic field, we can draw that as so. Here's the induced magnetic field. And now we can use our right hand. Coil rule. And if you use the right hand coil rule, you'll find that the flow of the current looks like this. Okay, so this is going to be the flow of the current. And so it is going to flow, for this question, left to right of the split ring commutator. Okay, so the answer will be option A. All right, so we'll move on from there. Question 15. What is the frequency of coil rotation for the alternating graph provided below? So here, guys, we know that the frequency is equal to 1 over the period. Okay. Now we're looking for the frequency of a quarter of a rotation. So looking at this, well, 1/4 of rotation is going to be 0.75 seconds. Okay. So that's our time taken for 1/4 rotation. And so you can divide 1 by 0.75 and you'll get 1.33 hertz. So there are 1.33 quarter rotations happening every single second. Answer is D. All right, let's move on from there now. So now we'll have a look at these short answer questions. Question number 1. A photovoltaic cell is an example of a power generation method containing unique properties that set it apart from other more traditional methods of power generation. A. Explain how photovoltaic cells work. So first of all, we should explain how photovoltaic cells, they obtain light energy from the sun. So we're not using mechanical energy like in our generators. Photovoltaic cells, or PV cells in brackets, obtain light energy from the sun. Okay, that is the first dot point. Second remark. What makes up our photovoltaic cells? We must talk about that as well. A photovoltaic cell is composed of multiple different layers. We have the N-type, we have the P-type, and we have the P-N junction in our PV cells. Okay, so let's describe the different parts of our cells. So PV cells are composed or made up of an N-type semiconductor that is negative, a P-type semiconductor that is positive, so P for positive, and a P-N junction between them. Okay? Now, the two junctions, or the two semiconductors, the N and the P-type, they're going to be linked through some sort of external circuit that the electrons flow through. So we can say that the electrons are able to flow from the N-type to the P-type via external wires. The last sentence here in this dot point is not super important for you to mention, but it's still good to mention just to make sure that you get the second mark. Okay, but the main point is listing the N and the P-type semiconductor, their charges, and also the P-N junction. Okay, those three components are the key components of our PV cells. Now, let's talk about how these cells actually generate a DC voltage. Okay. So as the cell receives light, energized electrons move to the N-type semiconductor, which leaves holes which are positively charged that move to the P-type semiconductor. Now this results in a DC voltage, hence a current. Now it's not super important for you to mention the fact that there's a DC voltage, but again, just to be on the safe side, just to make sure that your teachers are giving you the full marks, it's good to give them this extra information. Okay, part B, name one significant difference in the electrical output of PV cells compared to traditional methods of power generation. Okay, so PV cells produce DC instead of AC electricity. Part C, what devices are required to convert the output of a PV cell to one that is usable in modern Australian households? So that is our inverter. All right, let's move on from there. Question number 2. A single coil generator is currently in operation. A diagram of its design is depicted below. A. What is the minimum magnitude of the magnetic flux passing through this coil at any given point in time? That's interesting. So the minimum value of the magnetic flux, the minimum magnitude of the magnetic flux. This means that we do not consider consider negative values. Therefore, the answer will be 0 when the coil is in the horizontal position. What is the maximum magnitude of the magnetic flux passing through the coil? Okay, so this will happen in the vertical position when our coil is fully perpendicular to the magnetic field lines, and hence all of these magnetic field lines actually able to penetrate the area of the coil. So for this, guys, we have to look at the dimensions given and the values given in the diagram. Okay, so the magnetic flux would just be equal to 11.5 times 0.45 times 0.05, and that'll give you answer 0.026 Webers. C. If the coil is being spun at 60 Hertz, what is the magnitude of the peak voltage output? This is quite an interesting question. So for this particular question, guys, we have to figure out the frequency and use the frequency of the coil in order to obtain our time. Okay, that is the important thing. So first of all, let's figure out the time of a quarter rotation. So the time of a quarter rotation, what would this be? So the time of a quarter rotation, delta t, is going to be equal to the period divided by 4. Now the period is just equal to 1 over frequency. So 1 over 4 times the frequency, that will give you delta t. And we can do this and we'll obtain 0.0042 seconds. So guys, we can only have a look at the time of a quarter rotation when we're trying to figure out our change in flux and therefore our EMF. Now let's use our EMF formula. So the EMF is going to be equal to N times delta flux over delta T. Now N here, we have not been given N, so N will be by default 1. And the change in flux, the change in flux will just be 0.026 minus 0 divided by the change in time, which is 0.0042. And therefore the EMF would be equal to 6.2 volts. Okay, so again, just to recap, we are only looking at the quarter rotation, and therefore we must convert the frequency into the time of 1 quarter rotation. We cannot use the full period. Okay, that is very important to recognize. All right, so moving on. Part D. Will this electricity output be AC or will it be DC? Explain your answer with regards to the use of particular devices. Interesting. Okay. So first of all, we know that we have slip rings being used, and therefore the output will be AC. So the output is AC. Why? This is due to the use of slip rings. Third dot point. So we've gotten 2 dot points. How will we get the third mark here, guys? Let's think about this. We have so much space. For the third mark, we must actually explain what is the purpose of the slip rings. VCA requires VCE physics students to understand the purpose of slip rings and also the purpose of split ring commutators as well. Okay, so let's write this down. So what do slip rings do? Slip rings directly connect to each terminal of our coil, of the rotating coil, without changing connection. Okay? Thus, this results in an AC output. Okay? Perfect. So that is our third point. If you want, you can also mention how we do not use a split ring commutator here. And it would be a good idea to actually mention that, since devices is a plural. So this is actually implying that you must talk about more than one device. So we can also mention as well that if a split ring commutator was used instead, then the output would be DC. Perfect. All right, question number 3. A square 5-turn coil is passed through between two magnets as depicted below. Assume that the edge of BC is aligned horizontally with the edge of the magnets. The coil initially travels 25 centimeters in exactly 0.5 seconds at a constant speed. Okay, so we've got the displacement, we've got the time. So question A, what was the overall change in the magnetic flux through the coil? So in this particular case, we have to compare the distance that we're given with the distance or the width of our bar magnets, which is 15 centimeters. So right now, guys, the initial magnetic flux is 0. And so afterwards, after the coil leaves, the magnetic flux will also be 0 as well, wouldn't it? Okay, this is after 0.5 seconds. So how do we know this is after 0.5 seconds? Well, again, the distance we're told of travel, the distance of travel that we're given is 25 centimeters, which is greater than 15 centimeters, which is the width of the bar magnet. Therefore, the coil, after traveling 25 centimeters, must have left the bar magnet, and so therefore the change in the magnetic flux is nil. There is no change in flux. The answer is 0. Right, it's a 1-marker question, guys. So if you see a 1-marker question similar to this, you know that you can't overcomplicate a question like this, okay? It's meant to be a tricky question. Okay, you have to really think outside of the box a little bit, look at the diagram carefully, and think about the tricks that your teachers might pull out in order to, again, confuse students. Okay, part B. What was the maximum magnitude of the magnetic flux through the coil across its journey? So here we can now use our regular magnetic flux formula, since when the coil is actually within the magnetic field, then it will experience a maximum flux. Keep in mind, guys, that this 5 turns value, this is not used in the flux formula. Okay, so don't get the 5 turn value confused. Okay, and don't don't use that value. A lot of times the teachers they try to trick students into actually using it. Okay. So here we know the value of the magnetic flux, which in this particular case, we have the flux, the value of the magnetic field, which is 4 Tesla. It's hard to spot that there. Right. And then we can multiply this by 0.1 times 0.1. And we'll get the maximum value of the magnetic flux, 0.04 Webers. All right, let's now move on to the next question. Question C. Using answer to part B, calculate the maximum voltage induced in the coil across its journey. Okay, so for this, we have to look at, first of all, what is the time it takes? How long does it take for the coil to start out right outside of the magnetic field to just barely be within the magnetic field? Okay, that is what we're looking for. So how long does it take, guys, for this coil, which looks like this right now, okay, to end up looking like this? Okay, so what is this time taken? What is the delta T? That is what we have to look at. Now for this, the time taken for this to happen, guys, is going to relate to the distance traveled by the coil, which should be 10 centimeters. So when this side BC is shifted to the right by 10 centimeters, that's when the entire coil and the entire area is within the magnetic field. And that's just when the magnetic flux is the maximum. After this point, guys, the magnetic flux will no longer change, right? After the coil has been fully submerged in the magnetic field. So therefore, we must first of all calculate this time. So first of all, we have to look at the distance again. And we have to multiply this distance by this term over here, by these values, 25 centimeter and 0.5 seconds. Okay, so we can multiply those values, and actually it'll be easier to actually do this question if you take this in steps. So we can first of all figure out the speed, and the speed will be, in this particular question, 25 centimeters over 0.5 seconds. Which will be 0.50 meters per second. Okay, and then afterwards, we can simply use the speed, so 0.25 over 0.5 seconds, we can use the speed to figure out the time it takes for the coil to travel 10 centimeters. So the time is going to be equal to the distance over speed. So 0.1 meters, which is 10 centimeters over 0.5, which will give you 0.2 seconds. Okay, that will be the time. Now afterwards we can figure out the EMF from this calculation. So the EMF will be equal to N delta flux over delta T. N here is 5, time we know, change in flux we know. 0.2 seconds, multiply this by 0.04. And we'll get 1 volt. So the answer is 1 volt. Okay, so definitely a bit of a tricky question, this one. Yeah, definitely a tricky question. Okay, let's move on to question D. Determine the direction of this induced current the first time the maximum voltage is achieved, and explain your answer. Again, guys, the steps for utilizing Faraday's law and Lenz's law will be put up on the screen. You guys can have a look, and I recommend you guys put up those points, those steps into your cheat sheet in case you get a 3 or 4 marker question even like this. So here we know that we need to utilize our Lenz's law, because Lenz's law relates to the direction of the current. Well, we can't just use Faraday's law here because Faraday's law is too basic. All right, so let's get started. For the first step, we can go through the initial change in magnetic flux. So the change in the magnetic flux through the coil is increasing upwards. So let's have a look at this, guys. So we know that our magnetic field lines, and it's actually the wrong direction of the magnetic field lines, our magnetic field lines are going to be pointing upwards, aren't they? So the magnetic flux is going to be upwards. Now, as the coil approaches the magnetic field, the magnetic flux will be increasing, wouldn't it? So that's the first step, mentioning the increase in the magnetic flux. The number of magnetic field lines that are passing through the area of the coil increases as the coil enters the magnetic field. Now here for the first step, I didn't give the definition for Lenz's law since this is only a 3-marker question. If this was a 4-marker question, I would also, in the first step, mention the definition of Lenz's law too. But anyways, let's move on. So since the change in flux is upwards, hence the direction of the induced magnetic field is downwards according to Lenz's law. Even if you don't give the full definition of Lenz's law, it's still good to mention the law itself. Lastly, we have to use our right-hand coil rule. So using the right-hand coil rule, we can then determine the direction of the current. The direction of the induced current is going to be, we know, it's going to be clockwise. Okay, the fingers represent the current and the thumb represents the external or the induced magnetic field. Okay, so the current is going to be flowing clockwise. And how do I know this? Well, again, if I just draw this picture out for you guys, these green arrows, they represent the current's magnetic field, which is downwards. So you can take a right hand with me. Your thumb should be pointing downwards. And you can look at your hand from above and you'll see that the fingers are curling clockwise. And so therefore the current is going to be flowing from A to B to C to D. Since the corners have been given these labels, we should actually mention the current or using the terms or using the letters A, B, C, D. We should define the direction using those letters. Is A to B to C to D. Okay, or you can also say clockwise as viewed from above. However, it is good to still mention the current is flowing from A to B to C to D, since that is a more of a, let's say, concrete way of describing the direction of the current. All right, let's now move on to the next question. So the coil ABCD is now moved to a position position shown in the bird's eye view diagram. Calculate what the induced EMF would be if the coil were to move 5 centimeters to the right of the page at the speed of 1.5 meters per second. Okay, so guys, for this, you have to understand that if the coil moves to the right by 5 centimeters, then side BC is going to look like this. Okay, side BC is going to be just about to escape the magnetic field, but not quite. So we know that the magnetic flux initially is going to be a maximum. And we know the magnetic flux after the 10 centimeter, after the 5 centimeter traversal is also going to be maximum as well. So there is no change in flux. And if there's no change in flux, then that means that there is no induced EMF according to Faraday's law and Lenz's law. So Faraday's law is just part of Lenz's law, okay? So the induced EMF is 0, we can say. Okay, that will be the first mark. Second, the magnetic flux is maximum initially and is also a maximum after the coil travels to the right by 5 centimeters. Hence, we can make this the third dot point for the third mark. Hence, there is no change in flux. Okay. Which is required for an induced EMF. So we know, guys, from our Faraday's law and Lenz's law, you must have an induced, to have an induced EMF, you must have a change in flux. Okay, so EMF is proportional to negative delta flux over delta T. So that's the Lenz's law, which adds a negative. And so right now, we know that this delta flux term over here is 0. So therefore, this EMF will also be 0 as well. Okay, perfect. Now let's move on to the next part, part 4. So an electricity company is taking on a contracted work to supply electricity from a small gas-powered generator to a remote farm named Complete VEG Produce. In particular, they require the electricity to operate their 1 CRT television on site for watching the footy, which requires 90 watts of power. Okay, so we've got the power. Great. The initially constructed transmission system is laid out in the diagram above. The resistance of each cable is 7 ohms per kilometer. Okay, so this is the resistance, but only per kilometer, so we have to keep this in mind. Unfortunately, the farm found that they weren't receiving any electricity from their end of the lines. Explain using relevant calculations why this is the case. Okay, so we know that we have a required power of 90 watts. Let's see if this required power is actually met. Okay, so we should first of all have a look at what is the resistance and also what is our power loss across our transmission lines. So let's do some calculations. So the total resistance here, guys, of the lines is going to be equal to 7 ohms per kilometer, okay, times 55 kilometers times 2. Okay, 7 times 55, this is just the resistance of one wire, one total length of the wire. But we need to multiply this by 2 to actually obtain the total resistance across not just one wire, but also across the second wire as well. So you guys can see we have 2 wires here, right? So we have 2 wires, we need resistance in total, including both. So we end up with 770 ohms. Now afterwards, we can figure out the power loss. So second dot point for the second mark. The power loss is given by the formula I line squared times R lines. And so that will be equal to here, if we know what the current is, yes. Okay, so we can figure out the current using the voltage and the power. Okay, so we know the power is 240, so we know the voltage is 240, the power is 30, and so we can combine these values and use the power formula. Power is equal to V squared power is equal to actually I times V to obtain the current, which is P over V. Okay, so the current that's outputted will be 30 times 10 to the power 3 over 240. Square this, and you can multiply this by 770 ohms. And you should end up with the answer being 12 megawatts. Okay, 12 megawatts. Now let's think about this, guys. The power loss is 12 megawatts. Does this seem like it is something that can be handled by the system? Okay, the system is only receiving 30 kilowatts. So this is greater than the 30 kilowatts. So what we can say is we can say here that hence the supplied power is exceeded by the power loss. Okay, so hence no power is left for the VEG. Okay, perfect. Let's move on to the next one. So Complete VG decides to turn to a more trustworthy contractor to fix this issue and ensure they actually receive electricity. This new company suggests that two devices could be installed as a cost-effective measure of minimizing our power loss. Name these two devices. Okay, so the two devices that we have are the step-up transformer and the step-down transformer. These are the two devices. Okay, perfect. We can use both devices to minimize the power loss and therefore also make it cost effective as well. A Complete VG board member suggests switching the electricity source from gas to a solar farm situated a similar distance away in an effort to be more environmentally friendly. Explain why this would not be possible whilst utilizing the devices named in part B. Okay, so solar panels, guys, right, from the solar farm are really made up of PV cells. And we know that PV cells, okay, they will produce DC electricity. PV cells, or in full form, photovoltaic cells, which produce DC electricity. Okay, so that is the first dot point. Second dot point. Transformers do not function with DC electricity. Okay, third dot point. So here we have to go through why AC is much more, let's say, useful for transformers compared to DC. Okay, so transformers, they require AC as they rely on the process of electromagnetic induction, right, to induce electricity in the secondary coils. Okay, if DC was used, then there would be no change in flux. in flux, hence there will be no induced EMF. I know this sounds a little bit complex, guys, but let me explain this. So let's say we have two coils. Here's our primary and here's our secondary coil. Now the secondary coil is actually initially empty. What this means is that there is no electricity flowing through the secondary coil at the start. Okay, the primary coil though, on the other hand, guys, is connected to some sort of source, right? Now this source, if this electricity source is DC, what this would mean is that the current in the primary coil is going to be flowing in the exact same direction, right? It's going to be flowing in the exact same direction. And that will mean that the magnetic flux that comes out of the primary coil and enters the hollow area of the secondary coil, that is not going to change direction. The magnetic flux will have a constant direction. In this case, I'm drawing the direction as upwards. Okay, you guys can see how the magnetic flux stays upwards through the secondary coil. So how can you swap this direction of the magnetic flux? How can you make the magnetic flux go from being upwards to being downwards? Well, you can swap the direction of the red arrows that I've drawn. You can swap the direction of the current. And if you swap the direction of the current, okay, that's going to swap the direction of the magnetic flux. And that will change the magnetic flux and that will allow you to induce electricity in the secondary coils. The process of inducing electricity, guys, in the secondary coils uses electromagnetic induction. Okay? This process is very similar to, let's say, processes like wireless charging, for example. So wireless charging, okay, for example, your smartphone could be wirelessly charged. That too uses this process. And you require AC electricity for that. Okay, for there to be a change in flux. All right, so moving on. Complete VG decides to continue using the existing cables or cabling connected to the gas power generator and revises the setup as shown below. Now the turns ratio of T1 is 5 to 275. Calculate the difference in the power loss between the initial arrangement and the new setup. Okay, perfect. So now we have our transformers T1 and T2 that are placed. Now, let's first of all figure out, well, what is the current that is flowing through our transmission lines? So we know, guys, that the current that comes out of our power supply is 30 times 10 to the power 3 over 240. Okay, we can write that down, but then afterwards we need to figure out the current in the transmission lines. Okay, so 30,000 divided by 240, that will give us 125 amps. That's I1. So that is the current here, I1. But now we need to find, okay, what is the current that flows through the transmission lines? So for this, we need to use the ratios formula. So we know that I2 over I1 will be equal to N1 over N2, okay, which is equal to 5 over 275. Whenever you're given a ratio like this, guys, the first number is always N1, and the second number is always N2. Okay, so I2 over 125 is equal to 5 over 275, and we can then figure this out. We end up with I2 is equal to 2.27 amps. Okay, so that's our current. Now from this we can figure out the power loss. So the new power loss would be equal to, again, I squared R. So multiply 2.27 squared by the total resistance, which again is 770. And this should be 3977 watts. Therefore, the difference in the power loss is going to be quite big. So previously, we obtained our power loss of 12 megawatts. Now that wasn't an exact value. So you can obtain an exact value. So 12,03125. Okay, that's the exact power loss that we got previously. Okay, this should be saved in calculator. This is the old power loss. And now we subtract by the new power loss. And you'll end up with approximately 12 megawatts. Okay, so very interesting. The power loss difference is almost the exact same as the initial power loss. Okay, so there's a very big difference. It's almost like we reduced the power loss by 100% just by installing the initial step-up transformer. Okay, it shows you, how step-up transformers, they can greatly reduce the power loss and therefore save energy. Okay, Complete VG makes a special request for the voltage reaching the farm to be exactly 120 volts. Knowing this, what will be the turns ratio of T2? Give your answer to 3 significant figures. Okay, so that's another important point. All right. So we need the voltage reaching the farm to be exactly 120. So let's mark this here. 120 volts. And we know the initial voltage is 240. Okay, so let's first of all have a look at how we can figure out, well, what is this voltage drop across these transmission lines? Now, there's multiple ways to do this, guys. You can first of all figure out what is the current in the transmission lines and use the formula I times R to get the delta V. Alternatively, you can use the power loss formula in terms of delta V and rearrange for delta V. Okay, there's multiple ways to do this. Let's go through the simple way. So in the transmission lines, we know that the current, as we calculated earlier, was 2.27 amps. So therefore, you can figure out the transmission line's voltage drop. It should be 2.27 times 770. And that will give you the answer as being roughly 1,750 volts. Okay, so that is the voltage drop. Now, what is the voltage that we have just at the start, okay, of the journey of the electricity? So let's call this V line, okay? V line 1, let's say. V line 1. And then we can compare this to the voltage at the lines at the end. Okay, so what is the voltage of V line 1? Well, we know that the voltage here before T1 is 240. We can obtain V line 1, okay, using the ratios. So we can say that V line 1 is equal to N2 over N1 times V1, and we can multiply 240 by the ratio. And that will give us 13200. Okay, volts. So now afterwards, we can now figure out V line 2. So how much voltage is left over for the electricity after this voltage drop? Okay, so we are able to subtract the voltage that these transmission lines receive which is 13,200 volts that the transmission lines receive. We can subtract this with the voltage drop, and we'll end up with 1100 or 11,000, I should say, 450 volts. Okay, perfect. So now we have to repeat the exact same thing, but now we have to go the other way around. So now we have to figure out, okay, what is the number of turns of wire, or the ratio of the number of turns of wire that T2 must have such that we end up with 120 volts after T2. All right, so now let's do this using our ratios formula. Oh. So we can say here that N2 over N1, and this is for, so before we were dealing with T1, but now we are dealing with T2. Let's just write this here. So dealing with T2, we can say that N2 over N1 is equal to V line 2. We can just call that V1, just to call it V2 over V1. Okay, perfect. So guys, sometimes you have to use the exact same symbol for multiple different quantities, like we were using N2 over N1 for the two transformers. So this N2 over N1, don't get this confused with the N2 over N1 at the bottom. Okay, they're different because we're dealing with different transformers. Okay, perfect. So therefore, N2 over N1 is going to be equal to 120 over 11450. Yep, so we can divide that by 120 and we will get the answer 1450, roughly 0.0105. Perfect. However, if you guys notice here, they're actually looking for the ratio of the number of turns of wire of the primary against the secondary. So you actually need to reverse this and get the value of N1 of N2. And you should get roughly 95.4. Okay, so the number of turns of wire in the primary must be at least 95.4 times the number of turns of wire in the secondary. 95.4. Okay, so now let's move on from there. Okay, so we'll now have a look at question number 5. So question 5. A VCE physics student is experimenting with magnetic marbles and dropping them down pipes of various materials, placed perfectly vertically. The marble falls through as expected when using plastic, wooden, and rubber tubes, but curiously takes a longer time to come out of a copper tube. Okay, so copper, we know it can actually conduct electricity. Okay, it can conduct electricity. So the electricity doesn't want to be induced, and the electricity will fight back against what is causing it to be induced. Okay, so let's start this. Explain this phenomenon with reference to specific laws of physics. All right, so we have to mention, guys, our Lenz's law. So Lenz's law is applicable to this question. All right. So we can say that there is an increase in the magnetic flux through the area of the pipe as the magnet approaches the pipe. Okay, perfect. So now, according to Lenz's law, the induced current must flow in such a way such that its own magnetic field opposes the increase in flux. So therefore the magnetic field will be pointing in the opposite direction. Okay, so instead of, if let's say the magnetic flux was increasing downwards, for example. Okay, so perhaps we could, let's say, we might have, let's say, North Pole here, South Pole here of the marble, hypothetically. So imagine the marble is a bar magnet, and in that case, the magnetic field lines would be pointing downwards, the magnetic flux will be downwards, and therefore the current in the copper tube will flow in such a way such that its own magnetic field points in the other way, such that the magnetic field in this case will be pointing upwards. Okay, all right, perfect. All right, now overall, guys, what's the most important thing is that the magnetic field will exert an upwards force, magnetic force on the magnet. Okay, slowing it down. Now, another important thing to mention is that this does not occur, this phenomenon of inducing a current and therefore the current opposing the magnet's movement, this does not occur in the other materials that have been mentioned. In the other materials, as they cannot conduct electricity. All right, perfect. Let's move on. Part B. The students switch the marble out to a mothball of equivalent size. Explain what the most likely outcome would be. Well, you don't need to know much about a mothball, but a mothball is not a magnet. Okay, so let's write this over here. The mothball is not a magnet and it's not magnetic. Hence, Lenz's law does not apply. So the mothball will not experience a magnetic force, and will not fall down. Or not slow down, sorry, it will fall down, it will not slow down. Okay, question 6. A mad scientist is conducting an epic experiment. The diagram of it is depicted below. There are two metal rods that are free to move and connected to separate external circuits. Part A, determine what would occur if current was passed through in the directions A, B, and C, D respectively for the upper and the lower rods. Make reference to specific rules. Okay, so this question, guys, is actually coming from area of study 2. In this case, we know that the current is going to be flowing from A to B, so current will flow like this, and it will flow from C to D. So because the current is in the same direction, they'll actually be attracted to each other. Okay. All right. Now to do this, to prove this, I should say, we can use our right-hand grip rule on our rods. So right-hand grip rule. Okay. So let's first of all have a look at the rod at the top, and let's use the right-hand grip rule for that. Okay. So using the right-hand grip rule on AB. Right, so let's do this real quickly, guys. The thumb will be to the right and the fingers will curl like this. Okay, the fingers represent the current. And so hopefully you guys can see that the magnetic field will actually be pointing into the page at the location of CD. Okay, for the rod AB. So this is AB's magnetic field. Okay, magnetic field of AB. And you can see that the magnetic field of AB is actually going into the page at the location of CD. Its magnetic field is into the page at location of CD. Using the right hand, now we can use the right hand palm rule. CD will experience an upwards force, right? Let's do this together, guys. Fingers will be going into the page on YCD, thumb should be to the right, and palm will be pointing upwards. So CD experiences an attractive upwards force. And since CD experiences an attractive upward force or magnetic force, using Newton's third law, okay, you can also say that AB experiences a downwards force. However, this is only a 2-mark question. So for the second mark, we can say that hence they will be attracted. Hence they will be attracted to each other and they'll move towards each other. Part B, what would occur if the current directions were reversed? Okay, they will repel each other in that case. What would occur if the current was instead configured to run in the directions AB and DC for the upper and lower rods respectively? Actually, there's been a bit of an error there, guys. I was rushing through part B. So for part B, actually, there will be no change. So there will be no change since the current for the both of the rods will be reversed. So there will be no change since current flowing from A to B will then flow from B to C, and the current flowing from C to D will flow to D to C. So as long as the current is parallel, they will be attracted. But for part C, we have to now look at what will occur if the current was instead configured such that it ran from A to B and D to C. So now the currents are anti-parallel. Okay, so as the current are anti-parallel, the rods will repel now. Okay. Next stop point, we must now mention why this happens. this is shown by the right-hand group rule. Okay, and we can use the right-hand group rule on AB. Giving a magnetic field at DC being into the page. Okay, same as before, so the direction of the magnetic field for AB doesn't change. However, the current now changed, so the current is flowing from D to C. So when you use your right hand slap rule or your palm rule, your hand will look like this, the palm will be facing downwards, so DC will experience a downwards force. So using the right hand palm rule, DC experiences a downward magnetic force that will be repelling. All right, next question, question number 7. So here, a single turn coil of 0.05 meter squared in a cross-sectional area is being moved through a constant magnetic field. The graph of the magnetic flux versus time is shown below. Okay, now at 0.3 seconds, the entire area of the coil is contained in the magnetic field. Okay, so we know that. Now draw the graph of the EMF versus time on the space provided below. Okay, sure. So now for this question, guys, we have to look at our Lenz's law expression. So Lenz's law tells us that the EMF is equal to negative n delta flux over delta t. Now this n over here we can ignore because we're not looking at the y values. So we can simply just say that the EMF is proportional to negative delta flux over delta t. Now for those of you guys who are doing methods, you will realize that this term is simply just the derivative of the flux time graph. So you can think of that as the derivative or just the gradient of the graph. If you're not doing math methods, it's perfectly fine. Okay, this is just the gradient of the flux time graph, this fraction. So basically just look at the gradients of the flux time graph, and based on the gradients of the flux time graph, the steepnesses of the flux time graph, you can figure out, all right, what is the EMF and how does the EMF vary? Now we can first of all see here that we have linear flux time graph, okay? It's not a curve. Because of this, you'll end up with a constant delta flux of delta t, or constant gradients for the different sections. So let's divide our flux time graph into different sections. Let's call this section 1, section 2, section 3, and section 4. So for section number 1, we can figure out the gradient. And the gradient for section 1, roughly speaking, it's going to be 7 over, well, not roughly, but exactly speaking, it's going to be 7 over 0.3. So here, delta flux over delta t is equal to 23.33. Okay, you don't actually need to do this calculation if you don't want to, but this is for us to be exact. For section 2, the delta flux of delta t is going to be equal to 2 divided by 0.15, so it's going to be negative 13.3. For section 3, the gradient is 0, so the steepness is 0, we don't need to worry about that. And afterwards, for section number 4, we're going from 5 to 0, so 5 divided by 0.15, and we'll end up with the greatest steepness, which is 33.3. So this is definitely a bit of a tricky question, guys. You have to look at how the gradients change. Okay, now the exact values of the gradients, the exact values of the EMF are not important, but it's a little bit hard to sometimes eyeball the gradients. I mean, you can if you want to. If you're able to figure out, okay, which section has the greatest steepness, which one has the least steepness just by looking at the graph, then that's perfectly fine. But I know for myself I can't do that, so I would have to just look at the actual values and calculate them. Okay, so here for section number 1, we know that our graph has a positive gradient. So you have to add a negative in front of that, and therefore the EMF will be negative. And it will be a constant negative value since our graph is going to be linear, right? So the flux graph is linear, and I'll mark that as 0.3, and then we're going from 0.3 to 0.45, and at that point my EMF graph will look like this. The reason my EMF is smaller in region 2, okay, so the reason is smaller in region 2 is because the steepness of the flux graph is less in region 2 compared to region 1. Now region 3, what is the steepness of that? Well, it is just going to be 0. So we can just draw a flat line here. And then region 4, that's where you're going to have the greatest steepness of the flux graph. And remember, the steepness of a flux graph, that gives you the EMF. So we can mark this here, 0.90. Okay, so I'm just doing this roughly here, but I'm sure you can draw a proper scale. Now normally we don't like to have these horizontal lines being floating all over the place in physics. Normally we like to have them connected with vertical lines, and we can connect them like so, as shown here. Okay, perfect. Now by the way, for region 1 to region 4, I've considered the negative sign in front of the delta flux of a delta T. However, you don't really need to include the negative sign if you don't want to. So if you just want to look at the actual gradients themselves and not consider the negative, then you don't need to do that. Okay? All right, so part B. So given the information provided, explain the shape of each section of the flux time graph. Make reference to the movements the coil have made. Okay, could have made. All right, perfect. So in this particular case, we can see that our coil, first of all, it cannot rotate. Okay, so that's the first thing we can say. So in terms of the movement, the coil cannot rotate. If your coil rotates, then that means that the flux is changing in a circular function manner, in a sinusoidal manner. You'll get a circular function graph if your coil was spinning around. In this case, the coil cannot be spinning around. It must have just been moving in a straight line. Okay, so let's go through this, part B. So we can say that the coil could have been moved into the magnetic field until it is fully submersed at t is equal to 0.30 seconds. Okay, as the flux increases from 0 to a maximum. All right, so that's for the linear portion of the graph, you guys. So for the first linear portion of the graph, for section number 1, we can say this. The coil could have been just moved from being outside of the magnetic field, moved into the magnetic field until it is fully into the magnetic field at 0.30 seconds. And afterwards, it could have been moved out. Okay. So for section number 2, second dot point, then the coil could have immediately, without any further waiting, moved partially back out of the field. As the flux decreases between t is equal to 0.30 seconds and t is equal to 0.45 seconds. Okay, but not fully down to 0. Okay, so that's for this middle part of the graph, guys. So in this section, the coil could have just been partially moved out of the magnetic field, and but it would have just been kept there, being partially out of the magnetic field for some time in section 3. That's what we're going to be talking about. So for section 3, the coil could have just been held in place for a couple of seconds. Okay, afterwards, the coil could have been held in place just for 0.3 seconds. Okay, lastly, let's move on to section number 4. So here, we know that for section number 4, the magnetic flux is going from some value and going straight up to 0. So that change in magnetic flux going straight into 0, that must have been brought about because the coil was being pulled straight out of the magnetic field, and the number of magnetic field lines passing through the area would have dropped down to 0 in that case. Okay, so then the coil could have been completely pulled out of the field okay, from 0.75 to 0.9 seconds. Okay, perfect. So just to illustrate this situation here to everyone, let's say we have our bar magnets here, like so. Here's a north pole, here's a south pole, and the magnetic field is pointing downwards like this. So initially we could have a coil, and the coil could, let's say, have been moved in, okay, into the magnetic field, and let's say it partially, or not even partially, let's say fully, it could fully, perhaps, enter the magnetic field. Okay, so in that case, that is scenario 1 or section 1. Now for the next section, for section 2, this is when the coil has been pulled slightly out of the magnetic field like this. Okay, section 2. And then section 3, it just stays there. Okay, so you guys can see the red coil I've drawn, it just stays there, partially out of the magnetic field, but stays there. And afterwards, it's fully pulled out of the magnetic field, and the magnetic flux goes back to 0. Okay, now there would have been multiple different correct answers that you guys could have given for this question. You know, we don't need to change the magnetic flux just because or just through the entry of the coil into and out of the magnetic field. You could have also you could have also, let's say, changed the magnetic field strength itself as well. That's another way that the magnetic flux could have also changed. Okay. However, keep in mind though that in this question we are saying that the coil has been moved through the magnetic field. So, for whatever scenario that you would have chosen for part B, you would have had to involve some sort of movement of the coil. Okay. Like the last question, part C. What percentage of the coil was contained within the magnetic field at t is equal to 0.45 seconds? Give your answer to the nearest whole percentage. Very, very interesting. Okay. So here at 0.45 seconds, so the graph is not perfect, but this is at 0.45 seconds over here. At this point, we can see that the magnetic flux is going to be 5. Okay. However, at the peak, the magnetic flux is 7. So at the peak of the graph, that's when the coil, we can assume, is fully contained within the magnetic field. So all of the coil is within the magnetic field. Okay, now it doesn't entirely, oh no, it does, yes. So t is equal to 0.3. We are told that the entire area of the coil is within the magnetic field. So perfect. So at 0.3 seconds, at the turning point of the graph, at 7 Webers, that's when the flux is a maximum, and that's when the coil is fully in the magnetic field. Okay, so we know that the maximum value is going to be 7 Webers. And the value that is relevant at 0.45 seconds, that's going to be 5 Webers. So we can simply just obtain a percentage. Okay, we can simply say that therefore the percentage is going to be equal to 5 over 7 times 100, which is going to be 71%. Okay, now this, guys, assumes that the area is constant, right? So this assumes that the area is constant of the coil. If you guys are wondering what is the mathematical logic behind this, well, I can show you. So if you divide the 0.45 second by the maximum flux and times by 100%, what is this doing? Well, flux over flux. Well, what is flux, right? So flux is going to be equal to the magnetic field strength times the area as 0.45 seconds. The second flux is magnetic field strength times the area, the entire area. You guys can see how the magnetic field strengths cancel out. And so really what we're doing is we're dividing the area of the coil that is within the magnetic field as 0.45 seconds by the total area and multiplying by 100. So this over here, maximum, that's the total area that is relevant. Okay, so yeah, you're dividing that partial area, the area that's just partially within the magnetic field, okay, just the partial area, by the entire area. Okay, so if you guys found this video helpful, please comment down below, and please let us know what you like to see next. At Complete VCE Education, we are continually improving our services, and we continually want to provide more value to our students. All right, so hopefully this video was helpful to those who have watched.